All right, so we're doing more Chapter 11 practice problems. Last night you watched a video that kind of went through the first three colligative properties, which were vapor pressure, freezing point, elevation, boiling point elevation, freezing point depression. So before we start on this question, let me just back up. To vapor pressure. Okay, and we can deal with questions. So anybody run across questions they had on vapor pressure, boiling point elevation, or freezing point depression last night as you were watching the video? While we're waiting for questions to pop up, why don't you give me a number in the chat? One, I feel super lost and don't understand these concepts. Two, I probably get it, but would like to see more practice. Three, I feel very confident in understanding these concepts. Give me a check-in. Okay. That is very overwhelming. Overwhelmingly two. Yeah, we can go through the Van't Hoff factor again. Okay, let's talk through the Van't Hoff factor one more time. And then I guess we'll just go into practice problems because that seems to be kind of what you guys feel like you need. So here's the deal. In all of these equations that we're looking at, the change is always based on the concentration, right? They're colligative properties. And the very definition of a colligative property is that the property changes based on how much is there, not what is there, right? And so as a colligative property that depends on how much is there, the change is always going to come back to some measurement of concentration. For vapor pressure, the formula chi is dependent on the mole fraction. For freezing point and boiling point, it looks something like this. And the measurement of concentration is molarity. So let me show you the difference between looking at concentration in terms of a compound and looking at concentration in terms of ions. So let's go back to our crowd favorite, sodium chloride, right? Let's say we have 1 liter of 3 molar sodium chloride, right? So if we calculate the concentration, if we look at the concentration in terms of sodium chloride, or we can even do it this way. Let's back up. Let's say we put, 30 grams of sodium chloride into 1 liter. Tell me what that molarity is in terms of sodium chloride. I'll give you 30 seconds to set up that calculation and calculate the molarity of that solution for me. Molar mass of sodium chloride is 58.44 grams per mole. Okay. All right. Couple, you beat me there. Good work. Yes. So our solution is 0.513 molar sodium chloride. So that is the molarity in terms of the compound, sodium chloride, right? But when we know that when we take sodium chloride and we put it into water, sodium chloride breaks up into ions. How many ions does sodium chloride break up into? 2, right, 2 ions. And so if we are calculating molarity in terms of ions, we would have to take it a step further and go, let's see, 0.5. Well, actually, let me give you 30 seconds to do this. I want you to convert molarity out of sodium chloride and into total ions. I'll give you 30 seconds to do that. Okay, so 0.513 moles of sodium chloride per 1 liter of solution. Then we want to convert out of moles of sodium chloride and into moles of total ions. So for every 1 mole of sodium chloride or 1 compound of sodium chloride, you have 2 total ions. So you double it. So the molarity in terms of total ions would be 1.03-ish molarity of total ions. Hey, yes, again, some of you beat me there. Very good. Exactly, yeah. So this is why we need the Van't Hoff factor. For all of these formulas, my little picture's in the way of my pen. Let's try that again. Okay, so for all of these formulas that we talked about so far, vapor pressure, boiling point change, freezing point change, and then osmotic pressure falls into this category also. For all of these colligative property formulas, you either have to calculate the molarity based on total ions, or you calculate the molarity based on your compound and then multiply by the Van't Hoff factor, which is exactly what we did. We calculated molarity in terms of our compound, sodium chloride, and then we multiplied by our total ions. So we did that in our conversion. So you can do that. You can do that in your conversion and plug it in for your concentration, which so far is either your mole fraction or molality. Or you can calculate mole fraction and molality in terms of your compound and then just multiply the whole thing by the Van't Hoff factor. It's essentially what you're doing in your conversions anyway. You can either do it in a conversion or you can multiply by the Van't Hoff factor. Does that help with this Van't Hoff factor idea? Okay. And again, that's why I want you to run through like 1 or 2 examples of these. Like I said, the relationship, being able to describe the relationship is more important than being able to do the math. But it's helpful to cement that relationship in your head. It's helpful to go through a couple calculations and see if you're actually getting the right answers. Any other questions off of these concepts? Okay, so let's try this one. I'll give you a minute head start to read through it and start processing. Feel free to type questions in if you run into questions.
Would you use Raoult's law for this one?
Mm-hmm.
Is this okay.
Yeah, since you're looking for vapor pressure, that would be the one. Do you guys know the density of water at STP? It's 1 gram per milliliter. You have to know that in order to do this equation, in order to do this problem. So basically what I'm doing is I'm just trying to find moles of everything. What's moles of water, what's moles of glycerin, and then I can make my chi. Has anyone beat me to it yet? Okay, there we go. Hey, look at you guys. 1, 2, 3. All right, 3 people beat me there. Solid work. If you guys are off a little bit in your decimals, it's not a big deal, especially if you're showing your work. That's why you show your work, so that if we're off in decimals, I'll know where like the error came. When I do things on the calculator, I always hit second answer, and that way I don't end up with like rounding errors. If we're off on decimals, I'm guessing it's a matter of like where you rounded versus where I rounded. The rule of thumb is always just hit second answer. But even if you do that, like my calculator is going to cut things off at a different point than your calculator is. So even if we both just hit second answer the whole way through the problem, we're still going to probably end up being slightly off in decimals. And that's okay. Questions?
On the A test, if you're like a little even off, will you get it wrong?
No, they do the same thing. Like, and especially if you show your work. If you show your work and your decimals are off from theirs, it's fine. Even if you don't show your work, they have like a grace range where they accept answers within a specific range. So the rounding errors shouldn't make a big enough difference to actually cause you to lose points. Good question. Okay, I only have answers on Pear Deck from like 6 of you, which means there's like 12 of you who either have a question or haven't typed it in or are feeling very lost, and that's the majority of you guys. Unfortunately, I can't look at your work. I can't look over your shoulder to see what the questions are. You guys literally have to ask. But you're in the majority, so please ask your questions.
Why did you put the H2O on top instead of putting the glycerin on top?
Yeah, that's a good question. So it's not always clear, especially because they ask like, what's the vapor pressure of your solution? So if they don't make it clear which one they want the vapor pressure of, always do solvent. If they give you like down here, they give you the vapor pressure of pure water. So when in doubt, make your partial pressure match whatever they gave to you in vapor pressure. That's a good question. And going through this problem, I had to stop and process that too. Like, oh, do I do mole fraction of glycerin or do I do mole fraction of water? So I just made it match the vapor pressure that they gave. Good question. Okay, I'm going to delete this. If you want a screenshot, take it now. Or forever hold your peace. All right, let's try, hold on, let's try one of these. But is there one where we can avoid finding molality? Oh, the first one's kind of obnoxious because you have to convert mass percent into molality. The second one is also kind of obnoxious. Let's see about these. Oh, here, this is a good one. Let's do this one on top. Oh, both of these are good. These would be good test questions. So let's do both of these. I'll give you a minute to think about the first one, and then we can talk about it. Okay, when you have a guess or a question, make sure you type it into Pear Deck or the chat. All right, I see some good questions rolling in. Okay, so one question I saw was, do we need to calculate this? And for the first example, you could calculate it, but you don't need to. If you wanted to calculate it, then no, you couldn't, because you'd need the KF for water, and we don't have that. Yeah, so you cannot calculate this. Okay, so what you should be considering here is their concentration, right? Which one has the ones with the higher concentration should cause the greatest freezing point depression. The ones with the lower concentration should cause less of a freezing point depression. But it's not just their concentration, because every single one of these concentrations is listed in terms of the compound or the molecule. So what's the second thing that we need to consider in this problem?
The ions.
Yeah, exactly. How many ions it splits into. So your formula is going to be, oops, not an F. Freezing point change equals K times molality. But then remember, you also have the Van Hoff factor in here. So we don't know the K, but the K is going to be consistent for all of these. They're all aqueous solutions, which means they're all being dissolved in water. And so K is going to be K of water. So K is going to be consistent, and we can ignore it. That means you have to consider your Van Hoff factor, how many ions does it split into, and your concentration, which they give to you in terms of molality. Those two things are going to affect your ranking. I'll give you another 30 seconds. Okay, so what I'm doing currently is I'm multiplying the molality by the Van Hoff factor to figure out a new concentration, and that's what I'm going to base my ranking on. So calcium chloride splits into 3 ions. 0.05 times 3 is 0.15. Sodium chloride splits into 2 ions. 0.15 times 2 is 0.3. HCl is a strong acid. It's going to dissociate completely, splitting into 2 ions. So 0.1 times 2 is 0.2. Let me skip acetic acid for a second. This is an organic compound, probably some sugar, some form of sugar. I think that actually might be sucrose. Any biologists in here can verify that that's sucrose, which means it's not going to split up into any ions. So the molality of that is going to be the same, 0.1. Now, sodium or acetic acid is a weak acid. So it will, remember, weak acid split into some ions, but not very many. Most molecules stay as molecules. So that one's going to be slightly higher than 0.05, but it's not double. And so let's just make it slightly higher if we need to. I'm going to put an arrow on top of it just to remind myself that it'll probably be slightly higher, but not much higher than 0.05. Okay, so now I can rank them. NaCl is going to have the highest molality, so it's going to have the lowest freezing point. Maybe I should, because they're asking me to rank it in terms of freezing point. HCl is going to be next with 0.2. And then calcium chloride will be next with 0.15. And then glucose or whatever that is will be next with 0.1. And then HC2H3O2 is going to have the highest freezing point, the least depressed freezing point at 0.05 or maybe 0.06. Questions? Who beat me there? If the way they're asking you to rank it is confusing, you can also make a list like this, and then you can label like lowest freezing point or greatest. I keep doing an F there. Greatest change in freezing point, something like that. You can like label both sides of your ranking, and then it'll be clear like how you have ranked it. All right, questions on that one, or just move on to the next one? Very similar question. And you don't have to rank this. You just tell me which one has the largest increase. Alexis, you got it. Okay, so again, cobalt nitrate is going to split into 3 ions. So instead of being 1 mole per kilogram, it's going to be 3 moles of ions per kilogram. 2 moles of KCl, so this will actually be 4 moles of ions per kilogram. And then ethylene glycol is organic, so it is going to stay the same. So KCl is going to cause the largest increase in boiling point. And a couple, you beat me there. Nicely done. Yes. Good job, you guys. So those are types of questions that you can expect on the AP exam. You won't actually have to like chug out an answer. You know, you don't plug and chug and get me a calculated answer. You have to use the concept to kind of talk about the relationship in general. Okay, that is class time for us. I'll talk about osmotic pressure and then the Tyndall effect in the video tonight. And then tomorrow we will just review together live in class. So we won't have many practice problems to do together live in class. So make sure you bring your questions, bring problems, bring concepts you want to re-talk through, and we can do that in class too.